I think it's useful to periodically pause and reflect on what we've learned and where we're going. So now that we've reached the end of chapter 1, I think this is a natural point to do that. So, what have we really learned, or what was the point, I guess, of all of the stuff that we've discussed over the past 2 months or so? Well, I would characterize it as mostly a growing up sort of chapter. The point of everything that we've done is really to transition from what I will call example-based math to what is really rigorous mathematics. And I don't want to speak for you, but if your experience is like mine was, much of my middle school and high school mathematics was what I would call example-based math, which isn't really math. What do I mean by example-based? Well, if I had asked you, or if you had asked me in, say, 8th grade or ninth grade, to tell you what an even number is, or an even integer is, I probably would have rattled off a few examples. I would have said, well, even integers are numbers like 2, 4, 6, and 8, or maybe I would have said they're numbers whose last digit ends with one of those, or 0, and I would have said that's what I mean by even. But when we wrote proofs about even and odd integers, I invited you to say to yourself, this isn't good enough. This sort of heuristic reasoning where I list examples and trust the listener to infer the general pattern is really not intellectually satisfactory. I invited you instead to say we need to be somewhat more precise and give an explicit definition. Say, an integer m is even if m can be written as twice k for some other integer k. So again, if we asked the example-based student whether the square of any even number is even, perhaps he or she would try a few examples and say, well, 2 squared is 4, 4 squared is 16, maybe 8 squared is 64. So it seems to work in all of the cases, so that's probably right. Now that we finished chapter 1, I hope that you would respond to this sort of argument with a sense of unease and say, probably is not good enough. We require mathematical proof. And to prove that, you suppose m is even, so m can be written as twice k. Therefore, m squared can be written as twice k squared, which is, of course, 2 times the integer 2k squared. Since this thing in parentheses is an integer, the quantity m squared satisfies the definition of integer, where now k is replaced by 2k squared. So now we know with certainty from the definition that that statement that a square of an integer is even is actually true. Right? This is the transition we've been trying to make. I want to give a few other contrasts in the pre-chapter 1 way of thinking and the post-chapter 1 way of thinking. So perhaps the way that you were introduced to trigonometry in a geometry class was via this SOHCAHTOA thing. So perhaps someone drew a triangle on the board and said that, well, I don't know, sine theta is going to be the opposite length over the hypotenuse, where this is O and this is H. And I guess maybe, sure, you could think of that as a definition, but it's really not satisfactory, because you would ask, why have I made that definition? What's natural or interesting about this? Now that we finished chapter 1, the more mature, rigorous mathematics-based student would say, it is better to choose the most simple fundamental definition possible. So we define cosine theta and sine theta as the x and y coordinates of a point on a circle of radius 1. And once you've made that definition, we've seen this example, this other way of thinking about sine and cosine emerges as a consequence. So one of the things we've learned in chapter 1 is that the way a mathematician prefers to do things is to choose simple fundamental definitions which allow all of the other results to be derived as necessary consequences. You don't simply choose all of the consequences and state them at the beginning. They should all be derivable from a more fundamental set of axioms. In the same way, if I had asked you about exponentials before chapter 1, perhaps you would have said, well, these are functions like 2 to the power x, or 1/2 to the power x, and you could tell me what those look like. This one is perhaps some rising curve that looks like this, and this is some falling curve that looks like this, except my pen is a little screwy, like that. And now we would respond in the more mature way, saying, we have a definition of exponential function. It is a function which is either strictly increasing, strictly decreasing, or constant, and it satisfies this property f of x plus y equals f of x times f of y, and it only outputs positive values. And it's defined on the domain of the reals, of course. And now that we have that definition, you've seen we can prove things like that every non-constant exponential has an inverse function called the logarithm. So just to reiterate, the point of chapter 1 was this sort of growing up, that we now hold ourselves to the higher intellectual standard of stating definitions precisely and demanding to see rigorous proof of all statements or equations or results before genuinely believing them. So that's the reflection on chapter 1. What are we going to do moving forward? Well, I'd like to bring it back to the very first meeting we had. So, when we discussed limits in that meeting, I made this somewhat cryptic statement where I drew a picture where we had this black box called a limit, and I said you feed in some approximation, and the limiting procedure takes that approximation and gives you an exact value. And I said this entire procedure of feeding in the approximation, taking a limit, and getting an exact answer is what I mean by calculus. This is a very sketchy sort of explanation of what calculus is. And I've given you a few other sketchy statements. So without telling you what a limit means, I've asked you to accept this definition of E as the limit as n goes to infinity of 1 plus 1 over n to the n, where I kind of waved my hands and said just think about taking the number n very large and this approaches some number. I've also fed you this very kind of hand-wavy argument about the recursive formula for the areas of inscribed polygons, which you derived using the half-angle formula. And I said, well, if you take n larger and larger, that formula for an will get closer and closer to pi. So if you've really been understanding the point I've been trying to make over the past 2 months, when you think back about these examples that I've fed you, you should now say, well, those examples are very nice, and that's all well and good, but Christian, you'll have to do better. That's no longer good enough. You need to give me some rigorous definition of what you mean by this word limit if you want me to take you seriously. That's quite seriously. That's genuinely what I want you to be saying to me, that this heuristic, hand-wavy definition of a limit is not good enough, and if you've really understood chapter 1, there should be alarm bells going off in your brain that are telling you this does not meet my standard of understanding. I need a better definition of limit. And indeed, this is what we're going to do in chapter 2. We're going to have this famous epsilon delta definition, which will satisfy the hopefully what you have as a craving curiosity for what is the precise definition of a limit. And as a quick preview, I want to just explain why we might want to choose a careful definition of a limit like this. Because in the definitions of things like even and odd integers, the definition was fairly obvious. Something is even if it's twice another integer. There's really nowhere to go wrong in picking a definition like that. But as we move forward, we'll be discussing more subtle, nuanced mathematical notions like limits, and you'll see it becomes very important to choose the right definition if you want the object thus defined to have the properties you want. So what do I mean by that? So we spoke about this thing about ANs converging to some pi. So what could go wrong when we speak about the limit of these areas AN going to pi? Well, one thing that could go wrong is I've drawn this little dot just below pi, this purple dot here. So suppose this is a number which is very close to pi. So maybe it's like pi minus a very small number, like 10 to the minus 10 or something. Or maybe it's even 10 to the minus 100. So when I showed you the Python script that tried to convince you that these areas converge to pi, maybe it was the case that there's a very small error, so small that Python's rounding error just couldn't even detect it. We didn't have enough accuracy to detect it. Maybe those ANs were converging to a number like pi minus 10 to the minus 100, which is extremely close to pi but not equal to pi. And we never would have known from looking at the Python output. So we want a definition of limit which will allow us to rule out cases like this. In this case, we want to say the limit does not equal pi, and we want to be able to say with certainty that this case has not happened if we declare a limit to be equal to pi. Another thing that could happen is maybe those ANs, they do get close to pi, but they kind of wiggle around pi as n gets larger and larger. So maybe they approach pi, but as you keep increasing n, it kind of oscillates. Maybe this is pi plus some very small number, pi plus, I don't know, 10 to the minus 100 again, and it just keeps wiggling Maybe it goes to pi minus 10 to the minus 100. And it never really settles down to pi exactly. It just keeps wiggling around pi. And again, we wouldn't be able to detect this in Python, but we want a precise definition of limit which will rule this out. So if the limit as an goes to infinity equals pi, we want to know with certainty that this has not actually occurred. One final pathology is maybe the ANs actually do approach pi exactly, so it equals pi after a while. Maybe this line here, it approaches pi and hits pi, and it sits still for a while. Maybe the ANs reach pi, and then here it's exactly pi. But if you go very far out in n, maybe n equals a million, 10 to the 6 or something. Maybe so far we didn't even compute that many values in Python. How do you know that if you go that far out, maybe the area jumps away from pi? So it stays pi for a while, then jumps to something else like 4. And then if you go to maybe n equals 2 million or even 10 million, 10 to the 7th, maybe it jumps down from pi down to 3 and something like this. So this is something, again, a third example where we would not detect this numerically unless we computed a lot of values. But we want a definition which allows us to prove rigorously that if the limit exists, this is not happening. So why am I showing these? They seem like very unlikely, pedantic examples. But in mathematics, we want to choose definitions very carefully so that these unlikely but possible situations are ruled out by our definition. And the word for that is a pathology. So if you're a mathematician trying to choose a definition that captures a certain phenomenon, like a limit existing, and you accidentally choose a definition which includes things which you don't want, like these three X'd examples. What if we sloppily chose a definition of limit such that these three things satisfied the definition of limit? We would call those pathologies. They are things which satisfy the bad choice of a definition, but we don't want to be in the collection of objects with that definition. So this is why there's a lot at stake here. When we choose our definition of limit, we have to make sure that none of these strange-looking pathologies make it in to the collection of objects that satisfy the definition of a limit. And this is why we need epsilon delta. In my opinion, the epsilon delta definition is the cornerstone, the single most important and most profound idea in all of mathematical analysis, which is the branch of math that calculus is a part of. So it will take it takes time and effort to understand the definition properly, but I think it's some of the most well-invested time and energy that you could possibly spend. Okay, so that's all for our preview of Chapter 2.